check the program. I'll introduce you. The crowd goes crazy. We'll do a standing ovation, and then you can take it away. So our next speaker is Managing Director at Accenture Labs. Her name is Teresa. I'm trying to pronounce it right. Correct me if I'm wrong. Teresa Tung?
That's correct.
Okay, cool. Teresa Tung, Managing Director, Accenture Labs. You have a PhD in electrical engineering plus computing science at the University of California. Sometimes people say, Martin, that's not important. You don't have to tell that. If you know what you have to do for a PhD, that is something I need to mention. It's crazy. You're responsible for like finding the best breed of next-gen architecture solutions, and you evaluate their impact on the business by experimental prototypes and pilots. And today you're going to talk about how to maximize collaboration through secure data sharing. And as I read it, I think it's really interesting also from my non-tech background to see also, because we talked about it yesterday, in everybody's sharing data. Not everybody wants to share. There's a lot of security, a lot of businesses having their own agenda, but you're going to talk about how we can still look at that data, have it secure, learn from it, and still do our thing. That's my wrap up. I see you looking. That's not what I'm going to talk about. Yeah. Okay, ladies and gentlemen, I hope you're ready. If you have questions, ask them in the chat throughout. We'll do it afterwards. But for now, I say, Teresa Tung, the stage is yours. Have fun.
Thank you so much. And I'm hoping we can see each other next time. But hopefully you can see my screen as well. So I'm about to share. So as Marnik mentioned, right? So we know right now more than any other time how important it is to share data, right? Data is going to drive a lot of the decisions that are being made right now. And so we definitely have incentivized to do that, but trust, as we mentioned, do I actually trust the entities? We see a lot of social media companies, we see our governments, we see our insurance providers, even our employers. Do we really want to trust them with our data? Once you give it to them, they have it forever, and you want to make sure that they're using it for the right purpose. So that way that you really protect the trust of your data, that's going to be a way in which we compete. And we know some digital natives, they don't do such a good job in that, and we actually see that, like they're using our data for things that we might not have expected. Versus an example from Apple a couple years ago. Apple's really differentiated on how they trust, right? So the data within the iPhone, there was a local sort of attack, a terrorist attack in the US a couple of years where a husband and wife team actually shot up some of their coworkers. And, you know, the US government asked Apple, could you break the security within your phone so that we can actually see the data so we can fight this crime? And Apple chose at the time not to do this, because if they broke it for this one case, they're breaking it for many other things. And so they really had to stand up for trust and that protection. And it's really differentiated how I think about Apple and that particular capability. So this talk is about a new sets of technologies, a new sets of technology that really protect trust in a programmatic way. So it's not just about legal arrangements. It's not about ethics, but technology that allows us to really track and protect our data and how it's being used. So let's talk about that. I want to motivate with a case study. So this company called, so any large pharma, right? One of the most important things that they do is releasing drugs, and it's a very expensive, very time-consuming process. The whole process takes 10 years. The clinical trial by itself takes about 7 years. And so when each of the trial is set, ideally, we could possibly reuse, you know, some of that data for thinking about other things, right? How effective is this treatment? And the original study might have been looking at treatment in a general population, but I might want to reuse that data to say, how does it actually impact women or Asian women like myself, right? So could I do that and thus make, you know, the drugs better for everybody as a whole? And so this is good for everybody to do this. But then again, it's that issue of trust, right? Do I want to make sure my data, as I'm sharing it with others, are they using it for the right purpose? It should be the clinical trials. It should be for the experiments that you've agreed upon with the other company. And so could I use, you know, someone else's data to train my machine learning models or to find an insight off that data and to use it in a way that benefits everybody? And so this consortium called Melody, right? You can see it's a joint consortium with some of the largest pharma companies, Novartis, Merck, with a lot of the strongest technology partners like NVIDIA, and then some of these startups coming up, right? So it's bringing that together. And this particular case is actually the technology that I'll be going through later in the talk. So the technology is like cooking a meal without being able to see the ingredients. So we all know that data is encrypted at rest when it's stored. It's encryption at motion when you're transmitting it. But what happens when you compute? In the compute cycle, someone has to decrypt it, and then that's where you're running your algorithms that are either going to look at it in sight or do some sort of ML on it. So what if you could cook the meal, do that particular computation step without seeing the data? The data stays encrypted, or the data stays on premise in Teresa's control, so I don't actually have to worry about people using it for things I didn't. And that's exactly the set of technologies that I'm talking about and why it's so exciting. So let me give you 2 more motivation steps before I go in, right? So we know, again, the ability to access data is a competitive advantage. So this Harvard Business Review study found that 78% of companies, they're showing that the ability to easily access and combine data from external sources, it's very important for data-driven decisions. But only 23% said they currently are effective in this area. And only 15% were sharing data with their key vendors and suppliers. You can imagine with supply chains, right, as the world has changed. With supply chains, if we actually had them sharing data, we would have been able to react faster in a way that benefited society. But there's not these mechanisms in place. And part of it is due to trust, right? So when we talk about trust, it remains elusive, even with companies that trust each other. We're partners, we're suppliers, we're vendors. The lack of control over the usage of the data by the other organizations, it's just as important as a risk for companies. 42% that say that's a key issue why they can't trust each other. It's just as important as legal uncertainty over the data, which actually in this survey of the EU companies found that 54% said the legal issue was the only thing that was keeping them from sharing. And so these are barriers to overcome, and the risk of sharing data is sometimes higher than the potential value. This is how people perceive it, right? So Accenture research, we found that having a public data breach as a company, that the companies will see a 10% decline in their revenue for 6 months after the breach. And it could actually propagate over 2 years, right? So that risk and that fear is part of why they're not doing that. So once you give this to somebody else and that breach happens, that's also your data that's being shown. And many of us have felt this in a very personal way, right? As we actually have our personal data, sometimes when we give it to a company and then there's a breach, that feeling that you have, it's sometimes irreparable. So this capability that I'm mentioning again, it's called Multiparty Compute, is a class. The actual technology behind it is privacy preserving technology. And then we're going to go through that. That's the technology that we think will become something that helps these companies overcome these barriers that I just mentioned. So let me start with privacy preserving technology. This is what I've been teeing up the talk with. So let's start with the millionaire's problem. So let's say Bob, Carl, and Alice, they're all millionaires. They want to figure out who's richer, right? But they don't want to tell each of the others exactly how much money they have. So one way to do it is you could trust an intermediary, and you could say, we're all going to tell this intermediary how much money I have, and the intermediary will tell them, yes, Bob is richer. And this is how things work today. If we think about how a lot of companies are sharing data, there might be a common data lake. They might trust a common entity like an Accenture to be that intermediary. And then they figure out a common insight. So it's via certain legal approvals. It's via certain metadata management, looking at data lineage and data access, implementing your RBAC right. So that's how we do it today. But with privacy preserving technologies, there's a way to do this on encrypted data. So Bob, Carl, and Alice can all encrypt their data while it's in their control with the values that they have. And you still might have an intermediary who gathers the encrypted data or to make a sort of computation, but it's on the encrypted data and we get the result as to, again, who's richer, Bob, Carl, and Alice. And you would just say Bob is richer. And nobody in that chain, including that intermediary, would need to actually see the original values that Bob, Carl, and Alice had. So this is a simple lookup and a simple compare. And there's certainly a lot of value to that already. But imagine this capability done to a bit more advanced things and advanced problems. So let's talk about some examples of this. And this is really to allow data cooperatives. So if you have trust, this is actually what allows us to then have companies come together and work. So let me start with an example about financial services, something called traders and trading for dark pools. So dark pools is for very wealthy individuals. So let's say somebody at Accenture, let's say Julie wants to move a large amount of stock. And, one is she's monitored, so maybe not a good example, but she has so much stock, I imagine, that any action she make could actually move the market, right, when she sells something. And so dark pools is a way that allows this to be done. The bank, like a Credit Suisse or HSBC, will act as an intermediary. They'll take, Julie wants to sell the stock. This is what Julie wants for it. And they'll look across people who are willing to buy and make that connection. The bank does this. So the bank knows Julie wants to sell. They know how much stock she has. They need to know which price she's willing to offer. And the bank would need to know all the people who would actually want to buy this and which prices they're willing to accept. So you have to really trust that banking entity to do the right thing in that story. Well, with the privacy preserving computation and these data cooperatives, imagine a story where everybody encrypts. So even who Julie is, right? She would encrypt who she is. She would encrypt how much stock she wants to sell. She would encrypt the prices she was willing to sell it for. And all of us who might want to buy it would do the same. We would encrypt this information, how much we're willing to buy, how much we want to pay for it. And then now the cooperative, the role of financial institution is to actually just make those matches. And only when the match is made is this, shown, the fact that, let's say, Teresa wants to buy a certain amount for a certain price. So we never see the willingness of the whole range of data as far as what she was willing to pay, both the low or the high. And that might be more comfortable, right, in that situation. Let me skip to the last example because I'm going to show how this could work. So let's talk about telematics, right? So telematics and brakes. So let's imagine a supply chain where you have brakes manufacturers, you might have a telematics provider, and then we want to look at things like forecasting, when we need new brakes while preserving the privacy of the user. So maybe as Teresa drives, I don't necessarily want any of these people to know that I might speed sometimes, that I might take corners a little erratically. But for the improvement of brakes, it's really important to know people actually drive the way that Teresa drives, right? And so in that story, what if we could encrypt all this data? So each driver could encrypt exactly their data, and only that encrypted data is shared. The algorithm provider from the telematics manufacturer, that's encrypted too, because maybe it has their IP, their intellectual property with how they want to compute something. And only what's done for the manufacturer is just a forecast algorithm that takes the encrypted data from all of us, the encrypted algorithm from the telematics provider, and just projects forward that says, you order new brakes in this region, right? So we've actually built out something like this, and it looks as follows, right? So each car, each driver, we have something here. This is our data that has things around our brake and the engine, and it might have a location. In this case, it's France. Where am I in France? And maybe a different driver has a different sort of a view. And then the telematics company, all they have is the encrypted data, right? So they're seeing the encrypted values. They don't see the raw values to know maybe how aggressively I might drive or not. And then they might have external data like temperature, but the algorithm itself is also encrypted. And then what's shown to the brakes manufacturer is just a prediction that says, where do you need to order new brakes? And this has a lot of value, right? Because it's allowing the supply chain to work. My data is protected. The intellectual property from the telematics provider is protected, and we can still have the right results. And so this class, there's a couple of different techniques that allow us to do this, right? To work on encrypted data, to work on encrypted models and still get the right outcomes. right? So I'm going to actually go through each of these categories to show and illustrate what they are. So let's start with secure enclaves. So this is a hardware-based solution. And so in this case, party A and party B, first we have to agree upon what we're going to do. So in that previous story, I would have to agree on the telematics model or the telematics prediction that was happening. And then once we agree on that computation, that software is then run in a secure enclave. This is a hardware piece that is operated by an intermediary. And then that generates a public key that each of the parties A and B then encrypts their data against. And then the software then runs on the enclave on the encrypted data, and we get the result. So that's one way we've done things. And there's certain things that are challenges for this, right? So one, I think the most one is you still delegate the trust to that person operating the secure enclave. I still had to agree upon, this is the actual software. Someone has to implement that software model within the enclave, and I have to trust that they did the right thing, right? They didn't actually throw in some extra compute that I didn't plan for. And then also performance. This has a performance limit on the memory and the computations that are executed. But in many cases, this is programmatic trust. So if you could verify this and you can be part of that group that is really making sure that these models are programmed correctly, and you might be able to use legal steps to really make sure that happens, then this is a very good solution. Differential privacy is probably the one that you've heard the most about. So in this case, let's say that party C wants to use party A and party B's data for some computation. And so in this case, party A and party B are going to use differential privacy. They're going to take their data and add a little bit of noise to it so that you can no longer see the original data. It's pretty much sanitized. And then we take the sanitized data that has the same characteristics of the original data sets, and then party C can compute and get a result that is shared. And so this clearly has limitations, right? It certainly works with if your use case matches, but it only works with some use cases. The ability to add this noise and still have a meaningful result, it only works for certain types of computation. So there's a limited number of use cases this matches to. And then also there could be privacy breach attacks. So I might actually engineer my data that I submit to party C in a way that I can actually learn, how they're actually making the decision. And so there's challenges here too. So let me talk about homomorphic encryption. And so as I do that, let me give you an illustration of how maturity has come from federated learning, which you might have heard about. So federated learning, so let's say machine learning, typically we take the data, we might bring it to the cloud, and then in a data lake, and then you might actually have the machine learning happen there. Federated learning takes the model and the model that needs to be trained, and you push the model to the edge. So in this case, let's say on my phone, so Google, when they are doing the training for, the autocompletes of the words, right? So when you're typing things and it actually autocompletes you to the wrong thing, that's a learning model that actually does federated learning to figure that out. So pushes the model to Teresa's phone. And then on my phone is where that training has happened. And only the summary of the results is then pushed back into Google. And so in this case, this is a great first step, right? So none of Teresa's raw data was actually propagated within the data lake. It was just the learnings. And I would say the next step to that is homomorphic encryption. So homomorphic encryption does everything I just described, but the data is encrypted. So even the model that is actually running to learn is operating on the encrypted data. So let me now talk about what this could look like. So party A, it's going to need the results of someone else's data, let's say party C. And then party B, just like in the break supply and the telematics screenshots that I was showing, they might have a model that is a proprietary algorithm, right, that they don't want others to see. And so party C can encrypt their data. Party B will have an encrypted model. And only those encrypted results are then shared with party A, and party A can even add its own encrypted data to this. And so to decrypt it, you actually need the permission from all the parties, in the party A, B, and C, right? The person has the model. So here I can actually check that the model that I developed, maybe it's a machine learning model or it's a proprietary engineering model, that it's being used for the right purposes. So things like facial detection, you can imagine that you might want to control exactly who's using that and for what reasons. The data itself that's used maybe to train the model, that's also something that each party has control of. And so only when we all agree that this is the right result, the result is seen. So nobody had to actually be able to even see party B's model. So all their IP is protected and nobody would see the original data set. So that data is protected. And so, I mean, this sounds super cool. There are challenges. So one is performance. You can imagine running on encrypted models and encrypted data. That's a lot of compute. And so the math for this has actually been around for decades. But with the advance in computing, we can finally do this at a reasonable time for certain problems. And so the performance is an issue. It's typically an order of magnitude slower. There's computational complexity, right? So the types of computations that this works for, it uses a mathematical principle, homomorphism, same shape, right? Same shape of the formula. And so you can't do this for everything. You could do this for things like anything you do with SQL. You could do this for things like logistic regression, linear regression. But you're not going to be able to do this for all sorts of other types of AI and ML yet. Okay, so that's a limitation. The result and the precision is also something that for some of these algorithms that's a challenge, and it has to do with both the computational complexity and the performance. And finally, the multi-party schemas, right? To do this, we all had to agree upon the data schema and to make sure our data, before we encrypt it, actually looks in a certain way. So sometimes the value, as we all know, is actually in the data itself in its original form. So we really have to know what question we're trying to answer when we're taking this technique. But I think, it still offers a lot of cases, like I mentioned, with the supply chain, with the financial services and the trading, with even being able to look up, right, Teresa across different entities, let's say different government organizations, that this is all talking about Teresa. So maybe that match and that join is happening via homomorphic encryption. And then after they know this is Teresa, maybe the rest of the computations happen in a traditional way. But in this way, that person never had to have a trusted entity to see all the data. And we're still able to wait till we have a good hypothesis that, Teresa's the same person, and then make the case. Now we need to see the rest of Teresa's data because we think she's sick, or we think this treatment would be effective for her. Give us more data. So I think if you think about it as a multi-step, now it makes a bit more sense. Let me talk about secure multi-party compute. And secure multi-party compute is actually a combination of the different privacy preserving technologies. So if you take two of the different techniques beside this class, this is where you actually have secure multi-party compute. So things like homomorphic encryption, garbled circuits, secret sharing, it's layering these. But multi-party compute looks like this. So you have parties A, B, and C, and we want to set up these connectors. And so party A, B, and C will have that local computing capability in which you could do things like the federated learning, you could do things like the homomorphic encryption, and then you still have the aggregator and the orchestrator that takes that aggregated results and then presents something that's back for the whole party, right? So it's actually layering in some of the techniques that I just talked about. And so some of the same issues, right? So when you're layering it in, certainly you have the benefits that overcomes the barriers of each technique by itself, but there's other issues that might be involved, right? So scalability still remains, performance still remains. Some of the needs about protocol security, like how do you implement this? And there's complexity that remains. So hopefully it's not too negative though, right? I wanted to present a real picture for architects like you, but the capability to do the compute is really what's exciting to me. Like you have all these tools now that you can layer them in. And as long as you keep in mind, right, so and performance. So I'm not going to actually compute the whole machine learning algorithm, but taking the step to say maybe the part that I do first is just the join. Let's do a join that says take all this different data from the different parties. We're going to join and say, okay, these 3 people look like, there's something interesting about them. And then let's get the raw data in the second step. These are how you could apply that. So I'm going to end with one higher level story about trust, right? So I hope you're excited. I mean, I think I'm pretty excited by this new set of technology enablers that will allow us to look at programmatically protect data, its use, models, its use in ways that hopefully will alleviate the fears from consumers, alleviate the fears from enterprise. But then at the end of the day, right, it's really redefining collaboration and trust. So in that financial services story that I told in the beginning, today, again, I'm trusting this sort of money manager, right? I need to tell my money manager pretty much, he knows a lot of things about me, right? He knows how much money I have. He knows my ambitions, like if I want to buy a yacht or if I, am in debt and things like that. And he, today, especially for high net worth individuals, these people, they call, like they just know people and they call, they're like, oh, I think Marnik also, he's selling yachts. So let's make a connection, right? And if he didn't, it's really depending on this person, like the money manager, to make the best choice for Marnik and myself. And sometimes they have our best interest in mind, but you're actually putting a lot of trust on that other individual. So if we have this technology that now allow, these, some of our secrets to be more ours, or control over the data as to who I want to know that I'm in the market for a yacht and what I want to pay for it, or that Marnik is selling a yacht. I'm sure none of you know that, right? So I think all of this stuff we can actually think about programmatically, maybe replacing that role of the money manager, right? So we have a trust sort of capital that says, there's relationships, there's people who provide data that produces outcome, people who provide models that produce outcome. That's a different sort of trust that we're enabling, right? We're actually allowing these companies to now compete on their data, to compete on their models, compete on their trust. So hopefully this gives you a taste of this new technology. I did want to see if there's any questions.
All right, I'll jump right in. Thank you very much for the presentation, Teresa. And I'm super pumped to be in the yachting business. I always wanted to be in the yachting business. I want to own one. And now I heard that through this technology, I'm able to. So thank you for that. Someone says, it's not really, there are questions coming in. Someone said, I don't think it's really the first one a question, but someone says PPC sounds like mirror, mirror on the wall. So.
Sounds like magic, right? So I think I suggest you click on the link of the point of view that I'm sharing, right? So the math has been around for a long time. Accenture has actually open sourced a library called PyHeal to do PPC on via Python, and it wraps something called Microsoft Seal, which is the Microsoft C++ library for the same. And again, it doesn't happen with all types of compute. It happens with some. And as I mentioned, I hope I was honest, it's slow. But for things, let's say voting in the US, I don't know if there's a show of hands, but many people don't want people to know who they're voting, Trump or Biden, right? So this sort of thing would allow us to encrypt this and still get the right answer. It could be for things like I mentioned in the addition. So you can imagine things like if we all agree and we generate a random number as to what we change our addition factor by, and then we can sum it together and then remove the noise. We still get the right answer at the end, but then you've removed the noise, and you never knew who actually contributed to the original numbers. So I think these are things that you could kind of imagine how it could work, but I suggest you read the papers. It'll tell you how it really works.
For the rest, applause is coming in, so everybody's clapping. So it's good. People are asking for the recordings. So they probably want to watch it again. I have one more before I go. And it's also a question because I'm also allowed as a host to ask questions. I do it with every speaker. Tell me if this is a really dumb question, because like I said, I don't have the same background as the audience. So please be honest. But yesterday we had a panel discussion and we were talking with Jack Ramsey. I don't know if you know him. And he said that talking about this security in data, the trust between the people, the technology, the businesses. He says nobody's talking about it, but there's a big risk when the quantum computer is really there, up and running, and it's really a thing, then nothing will be secure anymore. I don't know what your opinion on that is, or what's your vision, or it's maybe a stupid question.
I work with quantum computers as well. So the breaking in of encryption, the factoring of two numbers, I think that's 10 years out. So the types of quantum that are 3 to 5 years out are things around something known as annealing, simulated annealing. These are things that solve optimization problems, right? So things like for planning logistics, right? So your trucks and where it's going to go. So anything you could write as a optimization logistics problem, that'll happen first. The factoring of two numbers, the size of the quantum computer today, the biggest number it can factor into the primes is 15. So we can all do that, right? I hope. So I think we're safe for the next decade.
All right. Okay, Jack, we're safe for the next decade. If you're watching. All right, I'm checking real quick because our time is almost up. People, a lot of applause. So I'm just giving you that. If you don't see it, it's always fun as a speaker to know. Definitely in online what feedback that you're getting, and also people are going to fill in the polls about the presentation. So I want to thank you also from the audience. Thank you very much, Teresa. And I don't know what time it is right there. Where you at?
Oh no, it's okay. It's 9:05. But I brought you guys right back on time.
All right, cool. Thank you very much. Have a great continuous of your day, and hope to see you physically next year.
Next year, yes. Thank you. Take
right,
care, guys.
Bye bye.